All right. Here are a few more examples of concave up and concave down. All right. So as you can see, these concave up parts would catch rain if it were to rain on the function, and these parts would deflect rain. They're concave down. A really good way to remember it is like concave up is like cup, and like, you know, a cup catches rain, you know. As you can see up here, we're just showing that it doesn't matter what the actual derivative of the function is. It doesn't matter whether it's increasing or decreasing or if it's stationary, right? And similarly here, as long as the curve is able to either catch or deflect the rain. The other thing you might notice is looking at the left-hand column, you might be able to see this notation here, d squared y dx squared. And again here, d squared y dx squared. So this here is actually the second derivative notation, right? Our first derivative, you might already know, we have dy dx. For our second derivative, we have d squared y dx squared. You don't need to know why this is, and to be perfectly honest with you, I don't even remember what it is. I don't remember where the squares go, but you don't need to. All right, if you're doing a question, you can just write y double dash, and then if they ask you to find the second derivative in this notation, you'll know what it means, all right? You don't need to remember exactly what it is. But all you need to know is that this represents the second derivative. So what you might be able to tell then is that when our curve is concave up, the second derivative is greater than 0, it's positive. When our curve is concave down, our second derivative is less than 0. So going back to our diagram here, think about it's concave down, our second derivative, less than 0, concave up, second derivative, greater than 0. So that graphically represents what we're looking at here. All right. Now, before we move on any further, I just want to make a quick point about what the concavity actually is. All right. So far we've been explaining concavity with reference to whether the curve would catch or deflect the rain. All right. But I want to actually give you guys a technical definition of what it is. So, concave up and concave down actually have a lot to do with not the derivative or, the gradient itself, but the rate of change of the gradient. And that's a mouthful, and I know. All right? So, think about it like this. Firstly, y dash is the gradient curve. So because the second derivative is just the derivative of this curve, we're finding the rate of change of this curve. So the rate of change of the gradient. All right. If that doesn't make sense, have a think about this explanation. When our curve's gradient is increasing and decreasing, is modeled by this curve, but the rate of change at which that gradient is increasing or decreasing is modeled by this curve. Right? So let's have a look, and we'll go along this curve. As you can see, it's quite steep down here. It's quite positive, quite steep. Right? As we're going up the curve, can you see how it's still positive, but it's flattening out? Flattening out, flattening out, flattening out until eventually it's flat up here. All right? So for this entire bit, the gradient was actually just getting flatter this whole time. All right? So it's really steep down here, It's going up, 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 and it's getting flatter and flatter and flatter until eventually it's just flat up here. So the gradient was actually decreasing. Even though it's positive, it's getting flatter, all right? So it might be, the gradient might be 1,000 here, it might be 500 here, it might be 100 here, and it's 0 here, all right? So even though it's positive the whole way, it's actually going down. All right, so now let's have a look across this side. The gradient now is negative, all right? And it's still decreasing because the curve here is flat and negative, so it might be like -5 here, and then it's getting steeper and steeper and more negative, you know, -10, -50, -100, -200, right? So up until right here, for this whole point on the curve, we have been decreasing. All right? So, although the gradient here is positive, it's getting less and less positive. All right? So for this whole point, the gradient is decreasing. It's going down. However, once we get to this middle point here, our gradient actually starts increasing again. So let's have a think about this bit here, right? So our curve is still going down. It still has a negative gradient. But as you can see, it's getting flatter and flatter. So at the beginning here, all right, it's really steep downwards. This might be -500. But then it's getting flatter and flatter. So it might be -100, -50, -25, 0. So even though it's still going downwards, all right, it's actually getting flatter. So the gradient is actually increasing because it's getting closer and closer to 0. All right? All right. Now, over on this side of the curve, our gradient is increasing. So it's flat here. It's now positive. So it's a little bit less flat here. Maybe it's 50. Then, as you can see, it's getting steeper and steeper. Maybe it's 100, 200, 300, 500, as you can see. So all on this side of the curve, the gradient is increasing. All right? So on the blue part, the gradient itself is decreasing. In the red part, the gradient, sorry, I should rephrase that. Scratch that. In the blue part, the rate of change of the gradient is increasing. In the red part, the rate of change of the gradient is sorry. In the blue part, the rate of change of the gradient is decreasing. In the red part, the rate of change of the gradient is increasing. All right? So the concavity of the curve is actually all about the rate of change of the gradient. So when the curve is concave down, the gradient is getting smaller and smaller that whole time. When the curve is concave up, the gradient is getting bigger and bigger that whole time. And then when we switch between them, it means the gradient has stopped decreasing and it is now gone to increasing. All right? So, let's move on. So, why is the concavity and the second derivative useful? Firstly, it's easier to draw graphs because we know about, the actual concavity of the curve, like what shape it is. I know a lot of people, when you're drawing graphs, maybe you struggle because even if you punch in the stationary points and like the intercepts, you don't actually know what the actual shape of the curve is. All right, so that helps with that. We can also use the second derivative in optimization problems, which hopefully you will remember a little bit from year 11. And we can also use them to determine acceleration. So they're very useful. All right. Now let's go through a few examples. So for this one here, I'd like you guys to pause the recording and have a go at finding the first and second derivative of the following. All right. So pause the recording, find the first and second derivative. So I'm going to start by finding the first and second derivative of this one here. Our first derivative is going to be 7x to the 6, just using our regular power rule. Our second derivative, so we're going to derive this one, is going to be 7 times 6, x to the 5th, which is 42x to the 5th. For part 2, remember whenever you have a any number down in a denominator, you always want to bring it up to derive. So we're going to use our index laws, and this will give us x cubed, right? So remember the index law, 1 over a to the m equals a to the negative m. So as soon as you swap a number from being on the numerator to the denominator, or the denominator to the numerator, whenever you swap where it is, all you need to do is you just need to change the sign of the index. So here our index was -3. Bringing it up, we just need to change the sign of it, which gives us x to the 3. So our first derivative here will be 3x squared. Our second derivative, so we're going to derive 3x squared, will give us 3 times 2, x to the 1, which is 6x. Righty. Now we need to find the range of values of x for which the curve y is increasing, decreasing, and concave up and concave down. So before we actually go ahead and do this, let's just identify what each of these words mean. So remember, increasing is when the gradient is positive. Decreasing is when the gradient is negative. Concave up is when the second derivative is positive. Concave down is when the second derivative is negative. All right, so let's go through and find the first and second derivative to start with. So our first derivative is going to be 6x squared minus 6x, take 12. Our second derivative is going to be 12x minus 6. Alrighty, let's find when these are positive and when they are negative. So, the first thing I'm going to do is I'm going to, or you can use inequality signs here, but considering that you guys potentially haven't learned them yet and they're not really within the scope of this lecture, we're just going to continue on with regular equal signs. Just a tip though, if you are looking for something to extend yourself before you get into year 12, do have a look at inequalities and solving using inequalities, because that is something that is necessary for year 12. Alrighty, so we're just going to let our first derivative equal 0. As you can see, this is just a quadratic. Alright, we can even divide this by 6 to get x squared, take 6, take 2, and hopefully we would be able to solve from there either by factorizing, hopefully, potentially using the quadratic formula, but hopefully at this point you guys should be able to factorize because that is actually a really good skill to know. So I'll go ahead and I'll factorize how I usually would a quadratic. If this isn't how you do it, that's okay. Everybody has a different method I've seen. So what I do is I take the a and the c terms of the quadratic, alright, and then the b term. So a is 1, right? So a is the coefficient of x squared, c is negative 2, so our number here is negative 2, b is negative 1 here. So all we need is we need a number that will multiply together to equal negative 2 and add together to equal negative 1. Alright? So, at this stage, I think negative 2 times 1 will give us negative 2, and negative 2 plus 1 will give us negative 1. So it looks like our two winners are negative 2 and 1, meaning that because this is a monic quadratic, as in we don't have any number out here other than 1, that just means that our x solutions will be these two numbers, alright, but the opposite sign. So instead of negative 2 and 1, we'll have 2 and negative 1. Again, if you need a rehash of solving quadratics, as I know a lot of people have kind of forgotten that you focus a little bit on their calculators, that's okay. Make sure you go and do that though, because there are a lot of times this is very much expected knowledge going into year 12, alright? So if you didn't understand how we did that quadratic just there, like quite a simple one, make sure you go back and learn that. Alright. So this tells us that our curve is equal, our derivative is equal to 0, 2 and negative 1. So all we need to figure out from here is on what side are those going to be negative. And look, you can do this using a table of values, but in my opinion, the easier way here to do this would actually just be to look at the curve. So our curve here for our gradient is a positive quadratic, meaning that the number outside of the x squared, 6, is positive, and that means we're going to have a smiley face quadratic. So our quadratic is going to look like this, where that's negative 1, and this is 2. Alright? So, without actually having to do a table of values, which is what you would have had to do otherwise if it was a more complicated curve, we can actually just look at what the shape of this first derivative is. So as you can see, our first derivative will be increasing. Right, I'll put the answer in a different color. It will be increasing when x is less than negative 1 and when x is greater than 2. So that's because, as you can see, these are the parts on which our curve is positive. It's above the x-axis. It has positive y values. Then it will be decreasing in this section here because this is where our gradient curve has a negative value. So this will be in between 1 and 2. Now let's move on to parts 3 and 4 of the question. So now we want to find when the curve is concave up and concave down. And again, all we need to do here, instead of using inequalities like I might otherwise do, let's just use an equal sign. We're going to let 0 equal 12x minus 6. So obviously we're going to get 6 equals 12x. and then x is equal to 6 divided by 12, which is a half. Now, instead of again doing the table of values, we can actually just sketch out what this curve would look like, because we know that this curve has a positive gradient of 12. All right? We know that the x-intercept is at a half, and we also know that it has a y-intercept of -6. Remember, like that constant at the end of a linear curve tells you the y-intercept. So this will be -6. Not that we particularly need to know that, but I guess it's just a bit helpful. All right, so that is our curve there. So it tells us that our second derivative is positive for this section here when x is greater than a half, and it's concave down for this section here when x is less than a half. All right, so for this question here, it mostly is just a rehash of information that you should be a little bit familiar with. If you were in a situation where you couldn't just kind of graph the curves and know what they look like just from looking at the parameters, then maybe in that situation, you would need to do a table of values. And just as a hint, make sure that going into year 12, if you really want to extend yourself, you have a look at solving equations using inequalities.